We are staring at two icy moons in the outer solar system that both harbor liquid water. Yet, they present entirely opposite and competing bets for the discovery of extraterrestrial life. One is a tiny world firing its ocean directly into space. The other is a massive, high-stakes vault holding twice the water of Earth, completely trapped beneath up to 25 kilometers of crushing solid ice. Before we can search for an alien biosphere, we have to understand the fundamental physical barricades that separate our instruments from the water. This is the primary paradox of modern space exploration. Jupiter's Europa and Saturn's Enceladus are frequently grouped together as ocean worlds, but treating them as similar targets is a serious scientific misstep. They are governed by completely different physical and energetic architectures. Europa represents a massive surface-driven system bathed in Jupiter's intense radiation belt, which bombards the outer ice to create vital oxidants like oxygen and peroxide. For life to exist there, those surface oxidants must slowly cycle downward through the thick ice shell to mix with chemical reductants at the dark seafloor. It is a massively shielded, high-stakes environment. Enceladus operates on the exact opposite paradigm. It is a bottom-up, seafloor-driven engine powered by tidal friction and hydrothermal vents, effectively mirroring the deep ocean ridges where life may have originated on our own planet. Because Enceladus has a surface gravity roughly 8.5 times weaker than Europa, its ocean does not stay trapped. It actively escapes into the vacuum of space through huge fractures at its south pole. Decades of data from the Cassini mission archives prove these plumes are not just water. They contain nanosilica, molecular hydrogen, and dissolved phosphates, the crucial bioessential building blocks required for DNA and RNA. We do not have to engineer a vehicle capable of drilling through miles of irradiated ice to test this environment. We simply have to fly a spacecraft through the venting spray and capture the chemistry directly. This extreme difference in accessibility is driving a major shift in how astrobiologists operate. In 2026, the Woods Hole Oceanographic Institution officially launched the Investigating Ocean Worlds project to map the exact fate of carbon on these moons. This collaborative effort will act as a critical decoder ring. When next-generation missions arrive, scientists need to confidently distinguish between raw abiotic chemical reactions and the genuine complex signatures of biological organisms. This framework is strictly essential for NASA's Europa Clipper. Executing its Earth gravity assist in late 2026, Clipper is explicitly designed as a habitability mission, functioning as an ice-penetrating CT scan of Europa. It lacks the instruments to scoop up water and directly test for microbes because Europa's ocean is locked away. We have to map the structural integrity of the ice fault before we can ever touch the water. But an accessible, venting ocean on Enceladus only matters if that water has existed long enough for life to take hold. For years, scientists assumed such a tiny moon would have frozen solid eons ago. To prove Enceladus was more than just a temporary flash in the pan, researchers had to find evidence of a stable, global heat engine in the absolute last place they expected to look. But before we can understand the thermal engines powering these worlds, we have to face the immediate physical reality of astrobiology in 2026. We are strictly limited by what our instruments can actually touch. The core problem with confirming extraterrestrial life isn't just predicting whether an alien ocean exists. It is about whether a spacecraft flying at high velocity can physically access the chemistry inside that ocean. When we look at Europa, we are looking at an impenetrable vault. Geophysical models estimate its protective ice shell is anywhere from 15 to 25 kilometers thick, completely sealing off the water below. Even if Europa's vast ocean is teeming with complex biology, its surface is heavily scarred and constantly bathed in Jupiter's intense, sterilizing radiation belt. It acts as a massive shield guarding its secrets from direct observation. This is exactly why the NASA Europa Clipper mission, which performs a critical Earth gravity assist in late 2026, is an ice-penetrating mission. It is designed to act like a planetary CT scan.
Clipper is an incredible feat of engineering, designed to determine habitability, but it lacks the instruments to scoop up water and test for microbes. It simply cannot bypass the physical barrier of that massive ice shell. Enceladus, on the other hand, breaks all the rules of planetary isolation. Because of its lower surface gravity and intense localized tidal flexing, it does not hide its ocean beneath an unbroken vault. Deep fissures at its south pole, known as the tiger stripes, are kept constantly open by orbital friction. The result is that highly pressurized ocean water boils straight out into the freezing vacuum of space. We do not have to invent a way to drill through miles of extraterrestrial ice. Enceladus is throwing free, continuous samples of its deep-sea chemistry directly into orbit for any passing spacecraft to catch. We already have the baseline proof. The Cassini spacecraft flew its mass spectrometer directly through these erupting plumes, capturing physical water droplets and running real-time chemical analysis before the material could degrade. Those free samples provided a definitive chemical inventory. Instruments detected molecular hydrogen, nanosilica, and complex organics, proving that the spray is not just melted surface ice, but pristine water from an active deep seafloor. By 2026, the Woods Hole Oceanographic Institution's InvOW project is actively mapping the fate of carbon using this exact plume data. They are establishing the baseline needed to distinguish abiotic chemistry from true biological signatures. While Europa forces us to guess what lies beneath its shell, Enceladus offers the low-hanging fruit of the solar system. It remains the only place where we can directly sample an alien ocean today. But there is a massive catch to this accessible water. Enceladus is tiny, and for decades, scientists thought this venting ocean was nothing more than a temporary, cosmic fluke that could never support life. According to standard planetary models, a moon this small should have lost its internal heat and frozen completely solid billions of years ago. To understand why astrobiologists are shifting their strategies today, we first have to look at why Enceladus was almost written off entirely. It comes down to a fundamental law of thermodynamics concerning surface area and volume. Small planetary bodies radiate their internal heat into the vacuum of space incredibly fast. At just over 500 kilometers in diameter, Enceladus has a high surface area to volume ratio, making it an extremely inefficient vessel for storing heat. For decades, historical thermal equilibrium models painted a bleak picture for its habitability. The calculations suggested that without a massive, continuous internal heat source, any subsurface water it possessed should have turned to solid ice billions of years ago. Europa, by contrast, is a massive geological vault. It is roughly the size of Earth's moon and holds twice the liquid water of all our planet's oceans combined. That sheer mass naturally insulates its interior from the cold. Furthermore, Europa is constantly kneaded by Jupiter's immense gravity, generating powerful internal friction. This top-down gravitational dominance makes it mathematically easy to model an ancient, stable ocean that has existed for billions of years beneath the ice. But in the search for extraterrestrial life, time is just as critical a variable as water. Habitability is not simply about having the right chemical ingredients. It requires keeping those ingredients stable in a liquid medium for immense stretches of time. On Earth, the genesis and evolution of deep-sea hydrothermal life required millions, if not billions, of years to develop. Because of its severe energy deficit,
early planetary scientists strongly suspected that Enceladus's ocean was a temporary, localized fluke. They hypothesized that a recent shift in its orbital resonance with Saturn might have triggered a sudden, temporary burst of tidal friction. Under this scenario, the ice had only melted recently, creating a transient ocean or a regional subsurface sea. If this flash-in-the-pan model was correct, the spectacular water plumes venting from the South Pole were just a brief geological phase. It meant the environment simply had not been around long enough for complex prebiotic chemistry to organize into living cells. Some alternative models tried to balance the energy budget by suggesting that radioactive decay within a rocky core might sustain small, isolated pockets of slush deep underground. But this still fell far short of a globally connected ocean capable of supporting a true biosphere. This historical assumption created a massive strategic divide in space exploration. Why would a space agency risk billions of dollars sending a flagship life detection mission to a moon that might just be experiencing a temporary, localized thaw? For a long time, the physics firmly favored Europa as the only serious, long-term bet. It is an unavoidable rule of astrobiology. Finding liquid water today does not guarantee that the environment has been stable long enough for biological evolution to take hold. To confidently target Enceladus, scientists needed undeniable proof that its internal heat engine was not just a localized anomaly at the South Pole, but a global phenomenon capable of keeping the moon geologically warm for a very long time. The math insisted Enceladus should be a frozen block of ice. But that entire baseline assumption was shattered in late 2025 when researchers stopped looking at the famous South Polar plumes and mapped the opposite side of the moon. For decades, our entire understanding of Enceladus was skewed by the spectacular water eruptions isolated at its south pole. But mapping the moon's northern hemisphere revealed a massive thermal anomaly where there should have been only dead, passive ice. In late 2025, planetary scientists finalized a comprehensive reanalysis of legacy infrared scans from the Cassini mission. By isolating the winter thermal emission data, they searched for any subtle sign of internal energy leaking through the thick northern crust. What they found was a surface approximately 7 degrees Kelvin warmer than passive solar heating models could ever account for. This heavily cratered, ancient northern terrain was actively radiating excess heat from deep within the moon's interior. This temperature anomaly translates to a steady internal heat flow of 46 milliwatts per square meter. Unlike the violent, explosive water plumes in the south, this northern activity is a quiet, continuous thermal conduction through solid ice. To put that measurement in perspective, it is roughly 2/3 of the average heat flow leaking through Earth's own continental crust. For a tiny, freezing moon in the outer solar system, it represents an absolutely enormous baseline energy budget. Researchers had previously measured about 19 gigawatts of heat escaping through the active southern tiger stripe fractures. When they combined that with this newly confirmed widespread northern leakage, the global energy budget of Enceladus finally snapped into focus. The data showed Enceladus radiating a total of approximately 54 gigawatts of heat into space. This specific metric is not just orbital trivia, it matches the exact thermal footprint required for a state of global equilibrium. It proves that the heat currently being generated inside the moon perfectly balances the heat escaping its surface. Saturn's immense gravity is flexing the entire rocky core, creating widespread tidal friction instead of just localized stress at the bottom. Because this internal heat engine is globally balanced, the subsurface ocean cannot be a temporary melting event doomed to freeze. The measurements confirm it is a remarkably stable, ancient environment that has existed over immense geological timescales. The exact thermodynamic pathways this heat takes remain incredibly complex to map. Scientists still debate how energy transfers from the deep rocky mantle, cycles through a global ocean, and conducts upward into the northern ice shell. Some geophysicists argue this northern heat could be channeling through specific, localized crustal weaknesses rather than uniform core heating. But regardless of the exact geological plumbing, the overarching proof of a long-term sustainable liquid habitat is now undeniable. To avoid any misconceptions, the North Pole itself is not actually warm. It remains deeply frozen under an ice shell nearly 20 kilometers thick, but it is radiating significantly more infrared energy than a geologically dead moon should. While the northern ice fault is far too thick for any spacecraft to penetrate, its thermal footprint proves the ocean below is permanent. This firmly establishes the southern fractures as the definitive, long-term exit point for ocean material. With a stable, ancient ocean finally confirmed by these thermal maps, astrobiologists are no longer just asking if Enceladus can hold liquid water. The critical next step is determining if it actively possesses the chemical building blocks for biology. With the North Pole proving that the ocean is a globally stable environment, the investigation shifts directly to the water's chemical makeup. This is exactly where Enceladus transitions from merely holding a habitable space to actively running a chemical engine. For years, planetary scientists debated whether the water trapped beneath the ice was just a cold, sterile reservoir. But when the Cassini spacecraft physically flew through the South Pole Plumes, its instruments tasted something completely unexpected: molecular hydrogen and nanosilica. Nanosilica particles are microscopic grains of rock that can only form when liquid water interacts with minerals at temperatures exceeding 90 degrees Celsius. Their presence was the precise indicator for active hydrothermal vents scattered across the Enceladian seafloor. Deep in the pitch-black ocean, hot water seeps into a highly porous rocky core. This interaction triggers an intense geochemical reaction called serpentinization, which fundamentally alters the rock and releases large amounts of free molecular hydrogen into the water column. On Earth, molecular hydrogen acts as the foundational fuel for entire deep-sea ecosystems. Methanogenic microbes consume this gas in total darkness, proving that biology does not need a single photon of sunlight if it has a steady supply of hydrothermal energy. But raw chemical energy alone is not enough to build a biological cell. For a long time, one crucial element was missing from the Enceladus inventory: phosphorus, the fundamental backbone of DNA and RNA. That uncertainty collapsed when researchers systematically reanalyzed archival data from Cassini's Cosmic Dust Analyzer. They discovered that the ejected plume ice grains are packed with dissolved phosphates, existing at concentrations hundreds of times higher than in Earth's oceans. Astrobiologists can now confirm that Enceladus contains all 6 primary elements required for life as we know it. It possesses carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, all actively churning in a warm, alkaline ocean. However, this profound chemical inventory comes with a severe astrobiological boundary. Finding complex organics and an abundance of molecular hydrogen is not the same thing as finding living biology. Every single one of these molecules and energy sources can be produced entirely by abiotic geological reactions without a single microbe present. We have firmly detected the biological food, but we have not detected the eaters. This epistemic gap is exactly why the Woods Hole Oceanographic Institution launched the Investigating Ocean Worlds project, which began its main operational phase in early 2026. The INVOW consortium is actively mapping the complex fate of carbon inside these alien oceans. By studying Earth-based hydrothermal analogs in the deep Arctic, the INVOW team is determining how organic signatures physically alter as they travel from a hot rocky seafloor up through a deep water column and freeze into the icy crust. This specific research will give the next generation of spacecraft the precise chemical fingerprints they need. It will allow our instruments to finally distinguish between a sterile, rocky reaction and a genuinely active biosphere hiding in the dark. The evidence is clear. Enceladus possesses a highly active, bottom-up hydrothermal engine. But its larger rival, Europa, lacks these easily accessible vents. Yet planetary scientists believe its ocean could hypothetically be vastly more productive. Which brings us to the biggest contradiction in this entire astrobiological search. How can Europa support a complex, thriving biosphere if its primary energy does not come from the seafloor? If Europa lacks the accessible, churning seafloor vents of Enceladus, how could it possibly power a thriving biological ecosystem? To solve this habitability puzzle, Europa forces us to look in the exact opposite direction for energy, up at the frozen surface. Europa orbits deep within Jupiter's intense magnetic field, subjecting it to a relentless barrage of high-energy particles. While this extreme radiation would be instantly lethal to any surface life, it acts as a massive, continuous chemical engine for the ice itself. As this radiation slams into the crust, it breaks apart frozen water molecules and recombines them. This drives a continuous, measurable production of surface oxidants. Spectroscopic mapping has confirmed that Europa's exterior is deeply saturated with trapped oxygen and hydrogen peroxide. In theory, this provides all the high-energy chemical fuel required to support a complex biosphere. If these oxidants can mix with reductants in the ocean below, they create the exact chemical disequilibrium that living cells use to extract energy. But there is a severe mechanical problem standing in the way of life. That vital oxygen is stranded entirely on the exterior, while the liquid water is locked far underneath, and the physical barrier between them is heavily fortified. The latest 2026 microwave measurements from the Juno spacecraft estimate that this rigid outer ice shell averages nearly 18 miles in thickness. That represents a massive structural bottleneck isolating the energy from the solvent. If that formidable vault of ice is completely stagnant, the surface oxidants will never reach the water below. Radar confirmation of an entirely immobile shell would strongly suggest that Europa's ocean is chemically starved, regardless of its immense water volume. This is exactly why planetary scientists are so focused on mapping Europa's heavily fractured, chaotic terrain. Geological evidence points to active, subduction-like processes, where massive plates of surface ice are laterally compressed and forced downward into the warmer interior. Advanced models of crustal delimitation show how this transport mechanism could operate on a global scale. Pockets of dense, salt-rich ice, weakened by tidal friction, can physically separate from the upper crust and sink entirely through the miles of surrounding solid ice. This establishes the framework for a true top-down biosphere. The ice shell acts as a slow geological conveyor belt, capturing the raw energy of Jupiter's radiation and dragging those chemical products downward until they finally melt into the dark ocean. It is a stark astrobiological contrast to our other target. While Enceladus relies on a hot, active core pushing molecular hydrogen up from the seafloor, Europa's primary habitability model depends entirely on radiation pushing oxidants down from the sky. But this top-down model carries immense uncertainty. We simply do not know the actual rate at which these surface materials successfully breach the ocean, or if the deeper, warmer layers of ice ultimately form an impermeable, stagnant shield. Europa might still possess active seafloor volcanoes to help power its deep waters. However, recent geophysical models suggest its rocky core could actually be geologically quiet today. Unlike the definitively proven hydrothermal vents of Enceladus, Europa's bottom-up energy remains purely theoretical. We are now faced with two completely opposed targets: a small, accessible ocean powered openly from below, and a massive hidden ocean powered mechanically from above. How do astrobiologists weigh these two vastly different bets against each other? When space agencies decide where to send billions of dollars, they are forced to weigh physical access against biological potential. Astrobiologists look at Enceladus and Europa not simply as icy water worlds, but as two entirely opposed strategies for finding extraterrestrial life. Enceladus has become the undisputed low-hanging fruit for near-term direct biological sampling. Because the moon actively vents its seafloor chemistry straight into the vacuum of space, passing spacecraft can capture fresh ocean spray without ever needing to execute a dangerous landing. But this supreme accessibility comes with a trade-off. Enceladus is tiny. Even with a globally stable ocean driven by hydrothermal vents, its total habitable volume is a small fraction of what exists around Jupiter. A smaller ocean could mean a sparser biological footprint that is harder to isolate. Europa, conversely, is the ultimate high-stakes gamble. It holds an ancient, dark ocean containing twice the liquid water of Earth. If biology took hold there, the sheer volume and top-down radiation-driven chemistry could theoretically support a much larger and more complex ecosystem. However, reaching that ecosystem is a profound engineering nightmare. Europa lacks the massive, consistent southern venting of Enceladus. To directly sample its subsurface water, future missions would need to deploy heavy landers, or eventually, nuclear-powered cryobots capable of melting through up to 25 kilometers of solid irradiated ice. This harsh logistical reality shapes the entire field of modern astrobiology. Do you target the tiny moon that sprays its chemical secrets freely into Saturn's orbit, or do you commit decades of engineering to forcefully crack open the largest habitable vault in the solar system? Yet, even if we solve the access problem, a deeper analytical obstacle remains. We currently lack a definitive biosignature that cannot be mimicked by complex abiotic chemistry. Deep-sea hydrothermal vents are perfectly capable of forging heavy organic compounds without any help from living cells. This is the exact problem driving the Investigating Ocean Worlds, or INVW project, out of the Woods Hole Oceanographic Institute. Moving into its operational phase in 2026, this multi-lab initiative is actively mapping the fate of carbon across both moons. The InvOW team is building a system-wide model to track how organic molecules are produced, transported, and degraded as they move from the rocky sub-sea floor up through the thick ice shell. They are essentially writing the biochemical instruction manual for future spacecraft. Without this carbon mapping, a probe flying through an Enceladus plume might detect a heavy organic molecule and falsely declare it biological. We must know exactly how background abiotic noise masks or alters true biological signals before those materials ever reach our orbital sensors. The ultimate risk for both targets is that life might be so sparse that our current instrument sensitivities will miss it entirely. Or conversely, we could discover that the deep ocean of Enceladus is completely sterile, churning out nothing but wet, lifeless rock. Astrobiology is not a zero-sum competition where only one moon is allowed to win. Both could be entirely barren, or both could harbor deep, dark biospheres. Regardless of the outcome, they definitively remain the two most promising targets for liquid water biology in our solar system. The strategic lines are now drawn. We know exactly where the water is, we understand how the thermal energy flows, and the baseline chemical models are finally built. Now we just have to send the machines to test those predictions. The scientific theories are locked in, and a specialized hardware is actively being assembled. But what exactly are the next generation of flagship missions going to do when they finally reach these alien oceans? Right now, the hardware designed to settle this debate is either actively flying through the solar system or moving into critical development. We are no longer waiting for theoretical models to improve. The physical tests are underway. The Europa Clipper launched in 2024 and is currently accelerating toward its final gravitational slingshot. In December 2026, it will execute a massive Earth flyby, passing just 2,000 miles above our atmosphere to gain the velocity needed to reach Jupiter by April 2030. But there is a crucial misconception about what happens when it arrives. NASA did not build the Clipper to find alien fish or scoop up living microbes. It is strictly a habitability mission, acting as a planetary CT scan for the Jovian moon. Its most critical instrument is the Reason ice-penetrating radar. This tool is designed to ping through the frozen surface and finally measure the exact thickness of Europa's shell, mapping the invisible boundary where the ice meets the dark ocean below. If the Clipper data reveals an ice crust that is entirely stagnant and dozens of miles thick, the top-down habitability model faces a severe crisis. It would mean the surface oxidants created by Jupiter's radiation have no physical pathway to reach the water. The Enceladus strategy, however, completely bypasses the problem of a thick ice fault. Because the ocean is actively venting into space, astrobiologists are designing hardware to catch the water directly, leading to the Enceladus Orbalander concept. Currently a central focus of NASA's planetary science planning, the Orbalander is undergoing intensive development in 2026 to refine its instruments and reduce mass. Unlike the Clipper, this proposed flagship is explicitly an astrobiology life detection mission. The Orbalander is designed to spend a year and a half orbiting Enceladus, flying repeatedly through the South Pole Plumes. It will capture the fresh ocean spray and run high-resolution mass spectrometry to identify complex organic molecules and potential cellular material. After exhausting its orbital sampling phase, the mission plan requires the spacecraft to descend and land directly on the fractured ice. From the surface, it will spend another 2 years running dedicated biosignature tests on the freshly deposited, refrozen plume snow. The ultimate challenge for both of these missions is distinguishing between abiotic chemical reactions and actual biology. A dead ocean and a living ocean can both produce complex carbon structures, and misinterpreting the data would be a catastrophic scientific error. To solve this, the Woods Hole Oceanographic Institution officially launched the Investigating Ocean Worlds, or InvOW, project in 2026. This team is systematically mapping the fate of carbon in Earth's deep hydrothermal systems to establish a strict empirical baseline. By understanding exactly how biological carbon signatures degrade and survive in extreme environments, the InvOW data will tell future spacecraft exactly what a genuine alien biosignature should look like when it hits a mass spectrometer. The search for extraterrestrial life has forced us to choose between two opposing physical realities. Europa offers a massive, ancient ocean that demands we penetrate miles of radiation-baked ice, while Enceladus offers a tiny, accessible engine venting its secrets directly into the vacuum of space. The instruments to read those secrets are finally being built. As we wait for the Europa Clipper to reach Jupiter, look up at the night sky and consider which ocean you would bet on, the impenetrable vault or the firing plumes.